Welcome. In this session, we'll explore the geometry of KKT points for a problem that has both active and inactive constraints. What we'll do is we'll look at a problem with three constraints. So this will be an objective that is simply 1/2 of the squared norm of the size 2 vector that comes in, and then we'll have these three properties. You don't have to write these properties down. We'll be making note of them later. And what we'll do is we'll consider these separately and then we'll consider them all together. So the objective function has contours that are simply circles. I will right now note what this function is. We'll need that for future sessions. Is that this function that has a vector argument is 1/2 of the squared norm of the argument. Let's look at problem 1. So problem 1 is the first inequality. So we have this objective function, and our first property is that 1, 0, 1 form times the argument minus 2 is less than or equal to 0. And that reduces to the first entry of the argument is less than or equal to 2. If we examine this, we see that this objective function has a minimizer at 0. That is, that's when the level is 0, and no level of a squared norm can be less than 0, so that must be the minimizer. So the solution is the unconstrained problem. That is, the user has provided us with a constraint, and that constraint simply isn't active at the optimum. So the implication, that implies that the Lagrange multiplier for this problem is 0. And we have to force that to 0 so that we can force the Lagrange function to be the same as the objective function, right? So our Lagrange function number 1 is the objective plus Lagrange 1 times property 1. And if we want the Lagrange function to be the same as the objective, then that has to be 0. So what does this look like? What this looks like is that the shaded region here is the set of feasible points, and we can see that the optimizer, the minimum of the unconstrained objective function, is in the feasible set. So when a point is an interior point of a constraint, that means that the associated Lagrange multiplier has to be 0. Now, let's turn to problem 2. In problem 2, we have this same objective function, and now we are looking at property function 2, and that was 0, 1 times the argument plus 1, and that has to be less than or equal to 0. So when we examine that, what that implies is that that reduces to the second entry of the argument vector has to be less than or equal to minus 1. And a constrained solution will then be we drive the first entry, we hold this entry equal, and we drive the first entry to 0. So the solution must be that W star for this problem has to equal 0 minus 1. And the implication is that the Lagrange multiplier for this problem has to be plus 1. That is, this constraint has to be active, and when it's active, we can see that if we made W2 smaller than -1, it wouldn't have a norm. The norm would be increasing, right? And so that means that this will be minimum when the constraint is exactly satisfied as an equality, and then if we treat that as an equality constraint, we can use either a primal method or a dual method, and we can then compute the Lagrange multiplier. So let's take a look at the geometry of this. The geometry is that the feasible set for this constraint is this shaded region. And as we just discussed, if we take a point that's inside this, that is an interior point for this, the vector norm won't be as small as it is when it's on the boundary. So for this problem, the constraint has to be active, and the solution is a boundary point of that constraint, and we can then solve it numerically or algebraically as an equality problem. Now, let's take a look at problem 3. In problem 3, we have this same objective function, and we now have the third property that we listed earlier. So that means that problem 3 is using property 3 of the vector argument, and this was 1, 1, W plus 5. And that is equivalent to saying that, so that's equivalent to, that would be W1 plus W2 is less than or equal to -5. And that would be a region, so that would look sort of like this. If this was if this is our coordinate frame, then this would have a normal that goes like that, and it would be a region that looks something like this. And we can see immediately that if we had W1 equals 0 and W2 equals 0, that is, if we took the unconstrained minimizer, that doesn't satisfy the constraint. And so if the unconstrained minimizer doesn't satisfy the constraint must be active. If the constraint is active, we can solve it as though it's an equality constraint, because anything that's in the interior here is going to have a vector norm that is greater than something that's on the boundary. So we want a solution that is a boundary point. That means that we want W1 plus W2 equal to 5, and when we do that, our solution is W3 optimal, that would be minus 1.5 minus 1.5, and for this, the Lagrange multiplier works out to be plus 1.5. Let's take our little hand drawing and let's look at it when it's illustrated by a computation. When we compute this in MATLAB, this is what we see, is that this shaded region is the feasible set, and if a point was an interior point for that feasible set, it wouldn't have a vector norm that was as small as a point that is on the boundary. And of the points on the boundary, the one that is here, minus 1.5 minus 1.5, is the one that has the smallest vector norm. You could also think of it as what point on this boundary has the lowest level for the objective function. Those would be equivalent ways of thinking of it. So what we've done now is we've explored one constraint that was always inactive. We explored two other constraints that are active separately. Now, let's combine them all and see what we get. When we combine all of these constraints, we have our problem 4. And problem 4 is this, and now we have the full, all of those properties have to be less than or equal to 0. So the solution, when we do this numerically, the solution is that our fourth minimizer is minus 1.5 minus 1.5. And when I do the computations, what I get is the Lagrange multipliers are 0, 0, plus 1.5. And we can see immediately that some things have stayed the same and some things are different. Here, in problem 1, the Lagrange multiplier was 0 because the constraint was inactive. In problem number 2, the Lagrange multiplier was positive because the constraint was active. And this constraint was also active. Now what's happened is we have 2 inactive constraints and 1 active constraint. So what's happened here? Well, it turns out that there are 2 reasons for a Lagrange multiplier possibly being equal to 0 in this. Let's take a look at a computer-generated image and we'll go through why the Lagrange multipliers are 0 for this problem. When we plot this problem, what we see is that the shaded region is the set of feasible points. And this is the intersection of our first constraint, which was that W1 had to be less than or equal to 2. And then our second constraint, which was that W2 had to be less than or equal to minus 1. And then our third constraint, which was this oblique constraint. And when we take the intersection of those 3 convex sets, we get a convex set. And now what we see is that the optimum is a boundary point, but it's a boundary only of the third constraint, and it's an interior point of the other 2. So now let's look over at those Lagrange multipliers. That first Lagrange multiplier here was 0 because that constraint was never active in this problem. The second multiplier is 0 because although it was active if it was the only constraint present, it's inactive because of the presence of the third constraint. So these constraints are interacting, and we can't solve a problem just by looking at one constraint alone. We have to look at all of the constraints together in order to get a full picture of the problem that we're facing.